Is it okay to start now? Okay, okay. Got it. Uh, then let's begin the stage one of Physics Fight 4. Welcome back to Physics Fight. Uh, in the first stage, Germany will report, and Greece will oppose, and Australia will review. As a tradition, the captains of the team will introduce the team and team members, starting from the reporter. Please, Germany.
Course, the jurors are accepting this. And this is Maxim, Rachel, Benjamin, Alan, and I'm Benedict, and we are together at Team Germany. Unfortunately, some of you may know, I would introduce our mascot horse, but it got stolen this morning. So we are searching for the team. Where is it now? But we are looking forward to a pleasant physics fight. Thank you.
And in Greece.
Hello, we are Team Greece, and our team consists of Anna, Dodo, Laura, Alex, and I'm Christos, and I wish everyone to have a nice fight.
Australia.
Hello, I'm Darius and we're Team Australia, and this is Brandon, Georgie and Quinn. And we wish everyone a good fight.
Now, jury members will introduce ourselves.
Okay, hi, good afternoon. My name is Tomasz Gruczyło. I'm a physicist at the University of Wrocław in Poland. I'm involved in the IYPT almost a decade, behaving as an independent juror, so I'm really looking forward to work with you and wish you all the best during that fights.
Hello, my name is Jamail, and I'm a physics student at the university here. Is it on? Yes, I'm a physics student here, master student. This is my first time jurying for the IYPT internationally, and I'm excited to see what you all have to show.
Hi everyone, my name is Silya. I'm team leader of Team Ukraine. I have been participating in IYPT for 4 years in the past, and now I'm studying theoretical physics and general mathematics.
Hello everyone, my name is Diana. I'm a physics PhD student at the University of Virginia. I'm also a former participant and a team leader for Team Georgia, and as you see, currently I'm acting as a juror. I hope you all have a really pleasant flight.
I'm Young Gi-yoon from Korea. I'm teaching physics at Jungwang University in Seoul, and I hope you good luck. Okay, let's start stage one. Stage one, Greece will challenge the problem to Team Germany. Please.
Due to problem number 8, levitating fluid.
We accept the challenge.
Problem number 8, levitating fluid, was accepted.
Test. Yeah, we wait. How do I switch like in this mode? How do I switch like in the mode? Setzt euch alle hin. Ja. Ja, ihr setzt euch hin, alles gut. Yeah. Okay, so I think I'm ready to start now. With that, hello and welcome to our solution of this year's problem number 8, the levitating fluid. Let's have a look at the task. When a container partially filled with liquid is oscillated vertically and air is injected at the bottom of the container, which you can see right here in our past demonstration video, we injected air at the bottom through a needle and the container is oscillated vertically. After some time, the fluid can levitate, as you can see here. The fluid stabilizes itself in a stable pattern. So, for the task interpretation, which are the relevant parameters to investigate today? So we have, of course, the shaker amplitude and shaking frequency determining the stability of the levitating fluid, as well as the container size in X and Y direction, and additionally the injected air volume. For the liquid properties, we have the density such as viscosity and surface tension. For our main investigation goals today, we're going to arise the first question: how does the liquid layer actually oscillate? So what are the patterns behind there? And when does it oscillate? So are there boundaries up on the stable oscillations? And yes. So first of all, for the basic principle, the very counterintuitive thought, how could an air layer form in the first way? So therefore we're going to take a look. If we have no oscillation, inject some bubbles into some air into the container. Of course, all of the bubbles will rise due to generated buoyancy force generated upwardly. So therefore we have no air layer will form. But what happens if we now actually have an oscillation downwardly? Therefore we're going to modulate the effective gravity. That means that we not only have the gravity but also the acceleration due to the shaker. So, and now due to that the buoyancy force is now proportional to that acceleration, we can time average that force and find out that there's actually in critical height below all of these bubbles will sink, and beyond that critical height all of the bubbles will rise. Therefore, if we inject then enough air volume and the oscillation is strong enough, some of the bubbles will rise and some of the bubbles will go down, and therefore an air layer is in the first place able to form. So now that we know that, let's have a further look at these liquid air and air liquid compositions. Note that the composition we have here, air liquid, is an unstable equilibrium. On the other hand, the liquid air composition is a stable equilibrium. That means that if we look at the liquid air interface, any small perturbation onto that surface would call in drainage and a full fluid collapsing. So, but how does the liquid then able to oscillate in the first place? Therefore, we're going to take a look at the so-called Rayleigh-Taylor instability, because we have a pressure difference both on these sides, and now effectively modulating the surface. If the effective gravity is going upwardsly, these the modes onto the surface of the liquid are going to increase, and if the effective gravity goes down, these modes are going to decrease. Therefore, because the negative part of the effective gravity is higher, this liquid can be stabilized. So for overall overview, we're going to start with the experimental setup, continuing with the first part, the stability analysis, and thirdly, looking at the stable oscillations, and concluding in the end. So for the setup, we used a laser distance meter as well as an accelerometer in order to measure the amplitude as well as frequency of our shaker system. The shaker was controlled by a function generating an amplifier over a voltage output. In order to control and precisely inject air into our container, we used a syringe pump, which you can see right here. And we also double-checked that our setup actually produces sinusoidal oscillations, which are in the first order given here. So our setup produces that indeed. So for different materials we use, we have different. We have different viscosity. We have different silicon oils with different viscosities, and we have different container sizes and shapes. So for our data analysis, we're using Python in order to find our critical amplitude based on the data from our accelerometer. And for the stable oscillations, we're using Tracker in order to track the fluid surface. So let's have a look at the stability analysis, and therefore we're going to plot some preliminary analysis. We're going to plot the amplitude over the frequency and see where the liquid falls down, and if there may be several boundaries. So if we look at it here, we can see that we have one lower boundary and one upper boundary. But what does it look like? Therefore, we brought a video of an increasing amplitude. You can see here that the surface gets very unstable, and at some point the whole fluid will collapse downwardsly. And then if we decrease the amplitude, at some point the oscillations can't anymore stabilize the surface, and all of the fluid will drain as a I've already explained, like in an unstable equilibrium. What is this due to? The lower limit is due to the Rayleigh-Taylor instability, where the lowest mode is the most dominant one and it is affected by gravity. And therefore you can see this fluid collapsing. And for the upper limit, we have the Faraday wave instability, which overcome where the inertia of these Faraday waves overcome the capillary effects of the waves themselves. So we took a video from the top and could see that we have some kind of Faraday wave pattern inside of our container. So therefore we now want to further investigate these wave patterns. Therefore we're going to take a look at the standardized Faraday instability. And assuming that we have a vorticity-free flow, we can represent the surface as a superposition of harmonic eigenmodes, where we have on the one hand the spatial structure determined by the harmonic eigenmodes and one time-dependent evolution term determining the amplitude. So first of all, we take a look at the harmonic eigenmodes, which need to be satisfied by the Helmholtz equation, and by constraining a Neumann and the no-slip condition, as well as in free surface, we can solve for the following eigenmodes, which are a product of cosine and sine functions, where you can see representative mode for 5-3 mode combination. So now that we've clarified the spatial structure, let's move on to the time dependency. Therefore, we're going to start with the standardized Navier-Stokes equation, and assuming that that we have a kinematic boundary conditions as well as the dynamic boundary condition of the pressure being tangential to a free surface, we can then assume that we have a rotational free, stationary, and incompressible flow, and solving for the potential of our fluid, which is interestingly growing with some kind of tangent hyperbolicus. And then solving out of this, we can separate the variables and solve for the actual differential equation describing the time dependency, which you can see right here, and as well as the dispersion relation connecting the eigenfrequency of the surface with the wave number. So let's have a look at this. We can see here that we plot the dispersion relation of the wave number. For smaller wave numbers, the gravity determines in this term, and for higher wave numbers, the surface tensions determine the surface dynamics. So let's have a look at the differential equation we had for our time evolution, which is actually just a damped Mathieu equation. And introducing these non-dimensional parameters, we can rewrite the Mathieu equation in the following form. Now, plotting the stability of this Mathieu equation based on Floquet theorem, we can see here that we have this first order resonance tongue, where below they have a stable oscillations and upwardsly we have unstable oscillations. So therefore we found in literature this equation for this instability criterion, and plugging all of this in, we can get the following equation for the critical amplitude, and plotting the fundamental mode as well as the respective mode for every single resonance tongue. We can then look at our experimental results and see that we have a very good quantitative agreement with our theory, where we can see clearly distinctive resonance tongue, typically for the Faraday instability on our upper limit. And so that means that below and over that curves, there's no levitation possible, where in between the levitation is indeed possible. So the same we did for a circular container, where we need to apply different boundary conditions. As you can see here, we are also able to quantitatively predict the upper boundary as well qualitatively the lower boundary. We also investigated the lower limit for the different viscosities, where we plot for different frequency, and can see here that we have for most of our experimental results also in quantitative agreement, because in higher viscosity increases the stability of the surface, therefore higher inertia effects are required in order to break off that surface. So now we fully investigated when the fluid layer is able to oscillate. Let's have a look at how does it actually oscillate. Therefore we're going to take several literature steps. So one can look at the container and the pressure and volume, assuming we have ideal gas law only for this air cushion. We can then write out the pressure, the complete pressure force, accounting for the atmospheric pressure as well as the gravitational force. And then we get the following equation for the pressure force, which just reminds us that this air layer actually acts as some kind of non-linear spring. That means we completely get the following differential equation, accounting for gravitational pressure as well as damping effects. So, because I said there's a non-linear spin, and we also have an external vibration to the system, we could possibly think about a resonance oscillator. So we can very shortly plot the resonance behavior of such a phenomenon, only theoretically, where you can see that this behaves in an approximately Lorentzian way with one resonance frequency. But nevertheless, we want to investigate onto the actual motion of the air layer height. Therefore, we are plotting a simulated curve where you can see in the beginning a stabilization due to the nonlinear pressure effect, and in the end, a steady state oscillation. The steady state is is reached when the energy input from the shaker approximately matches the dissipated energy. So we can zoom in onto the steady state oscillations and plot our experimental data we've achieved from video tracking, and can see that we're actually able to precisely predict this by fitting the damping coefficient. Note that here, interestingly, at some point, the oscillation of the air layer itself comes up with the exact same frequency of the shaker themselves, only due to some small inaccuracy due to the nonlinearities in our differential equation. So let's have a look also at these non-steady state oscillations in the beginning, where the whole fluid itself gets stabilized on their own. We can see here many things could remind us of a kind of Kapitsa effect, plotting FFT of that. We can also indeed see that we have one very fast vibration with a lower amplitude, and then going on to zero with a high amplitude and very low vibration, having in the same effect of a Kapitsa pendulum where the unstable equilibrium is stabilized as well. So now that we've also investigated that, let's move on to some further insight parts, where we're actually able to see that the fluid is not always oscillating completely stable. For example, we have here one phenomenon where we could see that the fluid in some kind of climbs up the walls and also simultaneously losing some of its volume or mass. So we can plot the trajectory, putting FH through it. And now think about what is happening here, because at some point the fluid gets unstable in some kind of way. That means the mass of the fluid layer gets reduced, and some of the fluid, a little bit of the fluid is falling down. So therefore, due to conservation of momentum, we just generate an upwards force driving the fluid to an increasing height. And when the complete mass is fall down, then of course the whole fluid collapses itself. So let's briefly summarize what we've did today. We've built a reproducible setup for the stability determination and use tracker for the venue analysis for the stable oscillation patterns. On our theoretical side, we used harmonic eigenmodes and Matthew equation in order to model the surface dynamics, and we used a nonlinear pressure model for the stable oscillations of our air liquid. So we are able to predict the stable levitation for different frequencies, viscosities, as well as an investigation of stable and unstable oscillation patterns. With that, thank you so much for all of your attention, and I'm looking forward to a pleasant fight.
Opponent has questions.
Okay, thank you very much. So first of all, I want to ask you whether you encountered any bubbles during their experiment.
We do not account directly for bubbles. We believe the.
Okay, yes or no? Did you encounter any bubbles?
No, we do not account for bubbles.
Okay. Also, I think you mentioned something that you use a syringe. So how did you inject actually the air?
So we use a syringe pump and then place the needle of our syringe in the end by hand in the container.
Okay, thank you. Also, in slide 47, I think you mentioned something about the OD part. Like, did you do both? Did you do an analytical integration? Why did you choose only one?
What you see here, where the Matthew ODE gets unstable for, is an analytical approximation for the first order resonance tongue.
Oh, and the rest was numerical, or?
No, so we made this model is analytically made, and the oscillation patterns are numerically.
Okay, thank you. Also, because I didn't quite understand, like you encountered multiple waves during the in between the layers, right?
Mm-hmm.
Okay. Also, in your experimentation, did you vary both the amplitude and the frequency, right?
No, so we fix the frequency and then pull down the amplitude and see at which point the fluid collapses. Yeah.
Okay. Not simultaneously. Generally, if you like varied both parameters.
So we varied the amplitude.
Okay. Okay. Also, can you tell me exactly what is the reason for the upper and the lower boundary that you mentioned?
So the one is due to So both the upper boundary is due to the Faraday waves inertia overcoming capillary effect, because the Faraday waves itself are stabilizing the liquid themselves, but when the inertia gets higher than the surface tension, then also the whole liquid column will fall down. And the lower boundary is due to the Rayleigh-Taylor instability, that at some point the most dominant wave mode doesn't get stabilized anymore, and which is determined by gravity, then falls down.
Okay, thank you very much.
Opponent, prepare opposition.
Okay. Okay, thank you very much for your presentation. So my name is Kaimakis, and I'm going to be the opponent for problem number 8, levitating fluid. So I think we're all familiar with the problem statement, and so I'll move on to the evaluation of the report. So first of all, about the theoretical part, I think we had some. It was a bit a complex theoretical model. I would like a little more elaboration from the report about that. They also, but they addressed the theoretical model for specific phenomena. Also, they did add theory to the corresponding graphs, basically to address phenomena experimentally observed. Basically, we saw also a good fit between the theory and the experiment. Also, they explained the boundary conditions that they used for their equations. But as for the negative aspects, I would like a bit more clear explanation of the phenomenon itself, like why exactly this layer starts levitating. Also, a big thing that I had a problem with is the height and the width of the levitating layer. Basically, I would like to see any more model about what exactly is the width of the layer that is levitating. Also, I think, again, slide 17, 18, I would like to go into more into the basic physics of the phenomenon because it wasn't very clear at the report. Also, in slide 46, 47, we saw a graph that had many curves. So I would like to. I think they used only a first order. I think they mentioned that, and I think this might be a simplification. So I would like to talk more about that in the discussion. They also did not explain. I think it's at the end of the presentation they did not explain why the fluid actually it rises or basically climbs up of the walls of the container. So I think that would be very interesting to discuss afterwards. But if we move on to the experimentation, I think they had a very clear demonstration of the visual aid, clear and basically how the phenomenon happens. I think we got pretty clear about that, the visual part. Also, they showed the experimental setup that in detail. Also, they with the graphs, they compared theory and experiment, and they had a very good fit, as I mentioned before. They described some inaccuracies that might have happened during the experimentation. And also they labeled graphs that account for phenomena in unusual values. Now, about the negative aspects, though, I think I asked in the clarifying questions that the syringe, basically the air was pumped in by hand, and I think this could have been improved. So I would like to talk about this in the discussion. Also, I think they only used basically high viscosity liquids. I think between 255 and 1,000. So why, for example, it's not possible with water? We didn't have a clear explanation about this. Also, I saw in their graph basically where they mentioned the upper and the lower boundary. They mentioned I saw that the errors basically decrease as we move on with the frequency, I think. Also, I think it's not possible to completely avoid the bubbles that could have formed in the liquid, and basically there could have been some volume change in that. Also, I think the vorticity flow rate is inconsistent in all of the liquid surface, basically. And in slide 33, I think the basically we all saw that the lower boundary is modeled at the middle, but in most of the videos we saw that it was like tilting to the right. So I'd like to talk about this more in the discussion. And basically, I would like again to show how the error bars were obtained, and they actually kept the frequency constant. And I think this could have been another parameter to vary. So I would like to invite the reporter to the stage. Yeah. Okay. So yeah. Okay.
So
the first thing, the first thing I would like to ask you is that I think in so when you mentioned that when you inject air, basically the bubbles go upwards due to the difference, of course.
Yeah.
But I didn't quite get a modeling of what exactly, how exactly is the width of the layer that is levitating? Like, what are the parameters that change the width, basically?
Okay, so as I again stated before, so we have not independently investigated the width of the actual liquid layer, but what could think about that if you think about that this critical height which you need to form this air layer in the first place is dependent on the acceleration, so on the amplitude and the frequency of our shaker.
Okay.
That means, for example, probably with higher frequencies, the liquid layer height would decrease, I would intuitively say.
Oh, okay.
But maybe when we stay at the bubbling, I want to clarify one first thing. I mean, you
Yes.
in your opposition, could I have a pen? Do we have a pen somewhere?
I think, but
Okay.
yeah.
Okay, so you said that we do not account for the bubbles in the actual
Yes,
liquid layer.
I would move
but
on to
if
that.
if
yeah.
we think about it, I mean, we can see it quite clearly in our initial problem statement. Here you have this liquid layer, and of course you can. I don't know if it's visible, but at some point there are some small air bubbles trapped in there.
That was my next point.
I believe that these have physically not too much of an influence because, of course, the air has a way lower density, and these effects are not that big, so that these actually have an influence on the oscillation of the liquid layer. So I mean, the only thing that we're changing with the complete whole mass.
Yeah, I understand.
That difference is, I believe, insignificant.
Yeah,
for the
I understand.
phenomenon.
But again, I think the bubbles themselves are a part basically that causes basically volume changes in the height of the air layer itself and the width of the levitating layer. So I think it's on the one hand, it could have been accounted like as a possible error, for example, or I think it's impossible, of course, not to have bubbles, and maybe it's too difficult to model it. But I think it could have been accounted and along test the width of the layer. But
So I'm saying again, I would not agree with that, but let's agree to
yes,
disagree.
yeah, exactly. Okay. Also, I would like to talk about. Can you go please to slide 33?
Yes. Of course, you can already start your.
Yes. Okay. So I think we can clearly see that on the on the right side, basically you model that this drop it's at the bottom basically, but in all of your experiments we can see that basically the tilting is one of the sides, usually the right one.
Yes,
so do
yes.
you have a physical explanation of that?
So okay, let's first of all come back why there's this slow mode. So in the Rayleigh-Taylor instability, you have the dispersion relationship,
Yes.
where you have one gravitational term, and then you have some surface tension term. So and that means for especially lower wave modes, the gravity determines, and only the lowest mode is a significant one.
Okay.
And we believe that we don't not see the fully thing because you think about that the complete fluid interface is like mostly unstable, and at some point then we have this lowest mode, the gravitational term mode, and it essentially like probably travels around, and the only place where it could possibly stop it is at one of the walls of the container. So that would be our physical intuition to explain why we don't see like this one mode in the middle.
Okay, and I'm sure that maybe any cause in the initial conditions could maybe like drop it to the left and the right, basically.
Possibly yes, but we mostly made sure that in our actual measurements that everything was
yes.
straight.
I actually brought that up because I think you modeled it basically as it drops at the bottom. But yeah, of course, I think we're talking here about ideal conditions or something. Okay, so yeah, I agree with that. Also, where you mentioned can you go back to the graph where you modeled the ODE? I think.
Yes, of course.
Where I asked you about the analytical integration. Yeah. Okay. So this graph here.
Yes.
Can you first explain why we have like more unstable parts? Like I'm sure there's a reason for that.
Okay,
Yeah.
so what we have here, so we've modeled so let's maybe come back again. We have the surface dynamics, and
Yes.
then we have one part which determines the spatial structure, so some kind of term xy, and then we have this term which determines the time dependency.
Okay.
And this will be modeled by this damped material equation.
Okay.
That means that it is in general a parametric resonance phenomenon, but we additionally have linear velocity proportional damping.
Yeah.
And what we do essentially is we plot the stability of such a material equation. So the material equation could be also found, like for example, in the linearized lato-lato, for example, in this year.
Yes.
And the parameters on the side essentially in some way represent the general amplitude and the general modulation of the system and the excitation frequency. And what you could see, like for parameter combinations, the system will behave. So essentially some kind of more complex resonance explanation.
Okay, so like higher order resonances.
Exactly.
Yeah.
Exactly. For example, what you can see is the first order resonance time, this is the second order, and this is the third time.
Yeah.
And we also believe that now that it's appropriate enough to only use the first order resonance time.
And like I think just now you mentioned like a parametric resonance, or like basically what's the parameter that's changing actually in the experiment that that caused parametric resonance?
So the frequency.
Oh yeah, so the frequency is like the
Yeah, because it's excited from the system.
yeah, that was my question. Also, can we like go back to slide 71?
71.
Yeah, now I would like to talk about the part where you mentioned basically the climbing.
Yes.
So first of all, I'm sure you you have a physical explanation of why it actually starts to climb.
Okay. Yeah. So our idea is that in the very first initial moment, the fluid layer in some kind of form gets instable, and a bit of mass is dropping down from here, dripping like this, some kind of way. And in the moment where a little bit of mass goes down, dm, of course the whole momentum of the liquid layer changes. Okay.
Yes.
And then then it goes up, and even more liquid drains down. And you can think of this actually like in some kind of way like a water bottle rocket.
Okay.
Because some kind of mass is getting out, and then we are generating upward force due to momentum change.
Like the thrust. Yeah. Okay.
So like in a very first order.
Yeah, but like the strange thing here is that it first of all starts to oscillate. I think at the beginning first, like it doesn't start to climb at the top. So. Like, is that caused due to disturbances, or is there like another physical explanation
extent
of that?
of knowledge, we believe this is just due to random perturbation on the surface, or possible that the system was not completely elevated straight, but we do not exactly know why this is occurring in the first place. We just wanted to qualitatively investigate on that.
Okay, yeah, I agree that this was an interesting investigation about the problem in the problem statement. Also, can you like go to slide 49 first of all? Yeah, I think we can clearly see here. I think that at the blue theoretical line, I think there is a sudden like discontinuity there that drops basically and then goes flat. Like, what's basically the reason for that? Because I think it's an important part.
So what we plot in the upper plot is the different mode selections for the amplitude frequency. So if we plot the whole thing, it would actually look with like separatedly kind of parabolic curves. So we have like this mode, and then we have this mode and so on.
Okay.
But of course in the phenomenon only the stable modes can occur, which are always the minimum ones. That means, for example, think about this going further down. This here is unstable, so therefore it would already jump down to this mode, and so on. And that is what we're essentially plotting in the blue line.
Yeah, so basically like another mode every time becomes a minimum.
Yeah, because it always reduces to this, because of an energetical minimum always reduces to the minimum mode, and that's why these could like not in practice occur.
Okay. Okay, I understand. Also, can you like go to slide 60 first of all?
16?
Yeah, 60.
60. Yes.
Yeah. Okay. I think experimentally you can see that in all your experiments, like it starts exactly at the steady state.
So we only So this what you can see here in the early part is like due to the nonlinearities in the pressure term.
Yes.
So we only experimentally looked at the steady state, because in that form we don't see the stabilization actually in experiment.
Yeah. So this is caused like due to the approximation that you do in the ODE part, I think.
Yes, exactly. Yeah, the nonlinear pressure model.
Okay.
Exactly.
And yeah, I think. I think that's all with the. Thank you very much for the discussion.
Thank you so much.
Yeah, okay. So, first of all, I think during the discussion we talked about a very important parameter that wasn't studied. I think this was the width of the layer that is levitating, basically, and of course, along with the height itself, basically the height of the whole air that is injected at the bottom. Also, I think that a part we talked about a little bit about the tilting that was modeled at the center, but of course it should have been like accounted as possible error as a discrepancy, maybe during initial conditions or something. Also, I think another part of the another important part was I think the bubbles, because as long as even if we want to, we can't actually avoid any of the bubbles. Of course, they can't be actually modeled, but they could have also been accounted as a part of the error analysis. And then we talked about the interesting part of itself of the levitating fluid that was climbing, and we talked about like explanation of that. Yeah. Okay. Thank you very much.
The dimensions of our container were differing between, no, sorry, mostly between 5 centimeters quadratic.
Say that again, sorry?
5 centimeters. 5 or 5,
As
5,
a
5.
square?
Yes, as a square.
Did you account for, so you mentioned sidewall friction. How did you find the sidewall friction?
The sidewall friction?
Oh, did you account for friction in the model?
Yes, so we have a dissipation term,
Yes.
and for this liquid layer oscillation, we're just assuming a velocity proportional damping.
How did
So
you find this? How did you determine this?
So we fitted that to our experimental
Okay, thank
dam.
you. Can you please, did you investigate the resonant frequencies of the fluid? And if we oscillate at that resonant frequency, does that relate to the amplitude of oscillation of the fluid?
No, we have only theoretically investigated the resonance behavior, but that would be definitely possible.
Opponent, do you think that the resonant frequency of the fluid is significant, and that if we oscillate at this resonant frequency, it will increase the amplitude?
I think I agree with that. Yeah, but I think it should have been investigated by the reporter himself.
How did you define the position of the fluid? Was it the center of the fluid? When you did your experiments, did you measure it from the center?
Yes.
And in your model, was this accounted for, that it was from the center of the fluid?
Yes, so we modeled it in a standardized Faraday waves model. Yes.
Opponent, how significant do you think the bubbles are to the motion of the fluid?
To the motion of the fluid,
Yes.
like when it's climbing upwards, you mean?
Yeah, in terms of the overall oscillations of it, how significant?
Oh, it's the overall, but it actually would change basically the width of the layer itself, and then it would create some discrepancies. I think in basically again, I think it's like a possible error because it's a thing that we can avoid actually, and when basically the bubbles are climbing when you inject it downwards.
Thank you.
Yeah.
Reporter, how did you measure the pressure in the system?
We did not measure the pressure.
You
in
did
the
not
system.
measure the pressure. Do you think this would be important?
No, I do not think so.
What do you think, opponent?
I don't think that right now pressure is an important part of the investigation, but it could have been accounted for.
Okay, thank you. Did you characterize features of the oscillating fluid such as the wavelength of the perturbations on its surface?
So yeah, so the whole modeling goes over the wave mode. So yes, so the wave number is.
And how did you characterize this? Was it measured experimentally as well as theoretically modeled?
No, theoretic investigations.
And did you validate this experimentally?
Yes, so with our stability condition for the upper and lower boundary, only indirectly.
Okay, thank you. Thank you. And they explain this with an unstable equilibrium. So if a denser fluid is above a less dense fluid, this would be in an unstable equilibrium, assuming the surface is completely flat. So any perturbation would cause it to collapse. However, when it's being oscillated, this equilibrium is made more stable, which allows the denser fluid to maintain its position above less dense fluid. So the experimental setup used laser distance and an accelerometer and a function generator amplifier. They explained the effect of amplitude of oscillation being too high, which causes it to collapse. So there's a zone where the amplitude allows it to maintain its oscillation, and then when it's too low, it doesn't allow levitation in the first place. They mathematically modeled aspects of the motion, looking at the wave number, the Floquet theorem, described the conditions which allowed fluid to oscillate in terms of some parameters such as frequency and amplitude, explained the steady state of the system, and compared to some experiments with theory. In terms of the opposition speech, they evaluated the report, evaluating the pros and cons of certain areas of the report with specific parameters and theoretical models. Mentions that there is not a clear enough explanation of the phenomenon and in terms of the height of the levitating layer, and that there is not a clear believe that the explanation of why the fluid initially rises was lacking. So for the strengths and areas for improvement of the reporter, in the report, their qualitative analysis was solid, and the ideas behind the phenomenon were well explained in our opinion, with the oscillation allowing the levitation of the fluid to be more stable. The mathematical model had solid complexity and appears to be well made with some good data agreement. However, their presentation was incredibly quick at times, which harmed the scientific communication, made it difficult to follow, and their explanation of the Floquet theorem and the relevant graph was lacking. The meaning of each axis was unclear. There was a lack of discussion and comparison between the theory and experiments. In the discussion, the reporter clearly explains many phenomena and demonstrated strong understanding there. The opposition. So in terms of their strengths in their speech, they correctly identified that the lower boundary is not exactly in the middle as in the experimental video, but the fluid itself is non-parallel, and evaluated some areas to improve in the report in some good ways. And in the discussion, they had some good clarifying questions. However, in this discussion, they did not provide their own opinion to much extent, which would have been more helpful. In the speech, they focused a lot more on the negative aspects of the presentation, instead of demonstrating their understanding of the positive aspects, and did not propose possible solutions to certain parts of it. So for discussion points, bubbles in the liquid was one point. The opponent believed that they asked how the bubbles were accounted for, and they believed that it was significant, and the reporter thought that the air bubbles don't have a significant impact on the model or the data because they're minor, and they disagree with the fact that they're significant. We believe that the bubbles do occur and that they may have some minor effect, but they're not that significant. So the tilting of the liquid, the opponent brought up that they did not model how the liquid was not actually parallel at times, and the reporter said that this was because of the Rayleigh-Taylor instability. And we thought it was unclear whether the shifting of fluid would have affected the measurement of the middle of the fluid, but we agree that this is explained partly by the Rayleigh-Taylor instability. There was discussion on the clarification on the climbing of the fluid, and we believe that the reporter's explanation of how the fluid climbed up was well done, but we do think that there's a missed out point here with the resonant frequency, because we believe that oscillating the fluid at that frequency will be a part of what increases its amplitude. And also, friction in the sidewalls was fitted as opposed to modeled. And thank you.
Okay, I'm sorry, I forgot my microphone. For the concluding remark, with the opponent, he pointed out some interesting points such as the bubbles. I still believe that these do not add to the actual phenomenon, because the mass and volume change they have, I believe, are minimal and insignificant, but still possible future investigation. We talked about the Rayleigh-Taylor instability and whether the lowest mode is in the middle or actually on the side, and we're trying to get a basic explanation. In general, the opponent covered a lot about the basic explanation parts, such as the upper and lower boundaries. So I want to clarify first of all that we did not pump in the air by hand. We only placed the end of the syringe in by hand and pumped in the air with a syringe pump. So that was controlled. Only the input was made by hand, which I believe is not significant because as long as you have it in the deep enough, pull it to the complete downwards, it's okay. Additionally, we talked with the opponent about the stability for the upper boundary, that only the minimal modes transverse are stable. And I want to add on the reviewer's suggestion onto the resonance frequency, that the resonance frequency, I want to first of all clarify that we have two different resonance phenomena happening here. One, we have a resonance from the air layer, and we have a parametric resonance of the surface, where the parametric resonance is due to the eigenfrequency of the surface itself. And the resonance curve I showed is for the resonance behavior of the air layer. So therefore, I also believe that this resonance phenomenon does not come into the account of the edge case investigations, because you see that the complete mean average height increases and not only the oscillationary mode, which would be typically for normal resonance behavior. And with that, thank you so much for the opponent and reviewer, and thank you that you made that happen. It was my reason that we rescheduled this fight. Thank you so much.
Now it's a time for questions from jurors.
Yes, so I have a question to the reporter. Can you clarify, please, what did you use in your experimental setup to oscillate the vessel?
I'm sorry, to oscillate what?
The vessel with the...
The vessel? So we had this we had a shaker, which is, let me show it to you. Here we have a shaker, you can see it down there, and this was controlled by a function generator and amplifier.
Okay, and what was the range of amplitudes?
The amplitude range was like for very low frequencies, we were able to generate amplitudes up to like 2.5, 3 centimeters, and the higher frequency we got, the lower, because the voltage of the amplifier capped at one point.
Okay, and can you move on to the slide number 49?
Yes.
Yes, so you mean here for low frequencies it is nearly the highest amplitude it could produce, yes?
I'm sorry?
Like here for low frequencies the amplitude is about 2 centimeters. It is on the like upper bound of the range.
Yes.
Okay. Yeah,
yes.
thank you. If nobody has one, I can ask. Okay, so can you move on to the slide number 12?
12?
Yes.
Yes, sure.
So here you explained us how the bubbles can sink.
Yeah.
So, could you clarify how the average of acceleration A can be non-zero?
So you could qualitatively think about this when you move, so the bubbles, when an oscillator moves downwards, if the container is moving upwards, acceleration is pressing more downwards than actual gravity, and other way around if you push them upwards. So, and also not only the acceleration changes, but this is one thing I neglected. They get compressed. The volume changes,
okay,
and buoyancy also
thank
is
you.
on the volume. Yes.
I have a question to the opponent. I would like to know your opinion on the thing that does the speed of pumping the air into that space is important for that behavior of the system.
The speed of pumping, basically?
The speed of pumping, basically.
Yes, I think that basically the speed of pumping. First of all, if you have like higher speed of pumping, basically you wouldn't have such uniformity like on the layers, basically. So. But then again, the speed of pumping, I think it isn't as significant as the other parameters, and this is why, like, the only thing that could create problems if you like increase very much the speed of pumping, again, is the problem with the bubbles, I think. So I think that it isn't such an important parameter like to take into account.
Okay, thank you.
Can you go to the slide 46 and explain a little bit more about the parameter Q that you investigate there?
What slide?
46.
46, yes. Yeah, so we have the parameters Q and A, and I've introduced them on the slide before here. So these are like these are just, so this down here is just a standardized Matthew equation. And this is, this is just algebraic formulations on how to get like the equation we recovered before into a standardized form. And Q, as you can see, Q like represents the amplitude of the system, and the modulation on the actual surface, and A represents the excitation frequency.
Okay, thank you.
Last question to the reviewer. What about the density of that liquid in that experiment has influenced the behavior? Just, yeah.
Density would mean, I believe, a greater amplitude of oscillation would be required, a greater frequency of oscillation would be required to reach the same amplitude.
Thank you so much.
Okay, then juror members will sum up their scores. You are ready? Scores for the reporter, please. 7, 8, 8, 9, and 8. Scores for the opponent. 6, 8, 7, 8, and 6. Scores for the reviewer. 5, 8, 7, 7, 7. Okay, for the scores of the reporter, we have 1 9, 3 8, and 1 7. So highest score 9. Could you explain?
Yeah, it is easier to explain the highest mark for me. Okay, so basically, I'm not really sure what to propose to do more. I mean, yes, you focused on the theoretical part mostly. Maybe there is something to do in experiment, but still the highest possible sum is greater than 10, so it wasn't that hard to obtain 9 with such solution. Also, I can see that some other judges could, jurors, sorry, could like lower grade for these 70 plus slides, I guess, but still you did a great job with to do it as clear as it is possible, and you were fluent in the physics and mathematics you operated, so that's it.
Mine is the lowest, and the lowest is 7. 7 is not a bad score. My partial grade is 3.5 for the report and 2 for the discussion, and I round up to 7. The overall presentation was very nice. The experiment was well done and analyzed properly. The only small thing I was not confident is that your own contribution was not highlighted enough, because this phenomenon is kind of known, and I mean, so if you have clear difference between the known analysis and your analysis, then it could have been better score. So that was my 7. For the opponent side, we have 2 8s, 1 7, and 2 6s. So for 8,
not typical situation for me to tell why I give the highest score. Okay, so basically you said like you did your best to give the opportunity for the reporter to clarify all unclear points of the report. I'm not sure you could propose something except of that. I mean, it was hard for you, I see it, to somehow oppose, criticize the physics presented, but you did your best to just give us a good discussion, which was interesting to listen to, and you really asked some questions I would like to ask also. So that's it.
I also think that with the current presentation, your discussion went pretty well, even though you were a little lost in the discussion. He was like more leading the entire discussion. For me, more of a problem was the report. when you were struggling to give him like some suggestions because his theories were correct and everything, somehow your report looked like you were focusing a lot on the negative points to find something negative in his report and really disregarded a lot of good that he has done. And somehow you had a lot of negative, way more negative points for this report than a positive. And then you had not much to suggest as improvement anyways. So I would love to see you acknowledge whatever good he has done as well. So that's why for the discussion you lost some points for me because you missed a lot of points that were well done.
Thank you. And for the review, we have 1.8, 1.5, and 3 7s.
So maybe I will start with my 8. First of all, we are always asked to give you some feedback on the partial points. So I was quite amazed by the first part of the presentation, question asked. You were really asking questions that were clarifying all what's going on. So I gave you 1.75 for that part, 2 for the other, 1.5 for the other, and 1.25 for the last. So it sums up to 7.5. So I have to round this, and I'm more eager to round it up. And also for that, that on your presentation, you've got a very elaborated review of reporter and opposition. So that convinced me to simply round it up.
Mine is 5, and my partial grade is 1 for question, 1 for review, 1 for review of report, 1 for review of opposition, and 1 for discussion analysis, and 0 for missed points. And I think the overall review was good, and it was well balanced, and it has all the components for the review. But however, the time management in the end was not perfect, and that was why I didn't give point to the missing physics. And the prioritization was a little bit weak, so I mean, in my opinion. So that was the reason for my score. Does any student want us to explain some specific scores? Let us know, because your feedback can lead us to give you more explanation. No? Okay. Thank you. So let's end the stage 1, and we will have a 10-minute break.